Welcome back, everybody. In this video, we'll be starting section 3.7, which is about rational functions. And basically, this is going to be the last kind of class of new functions that we'll deal with in this chapter. We spent a long time working on polynomials and polynomial functions. Rational functions are built out of polynomial functions by division, basically. So as we'll see, this is kind of like taking the step from integers or whole numbers to fractions when you're working with just numbers. So that's basically what this section is about, is what do you get if you divide two polynomials, what kind of functions are obtained, and how do their graphs look like, and things like that. So we have kind of an example to introduce the idea. So there's a story that goes with this. Suppose that you order 4 pizzas for a party. Let P of n be the amount of pizza each person gets if there are n people at the party. So thinking about it, this is going to always include yourself, okay? So if it's just you, then how much pizza do you get? Well, you're going to get all 4 pizzas, right? So we're going to fill out this table down here. So if there's 4 pizzas total, if there's one person, then that one person gets all 4 pizzas. If there are 2 people, then the 4 pizzas are divided by 2 people, and so each person gets 2 pizzas. If there are 3 people, then we have 4 pizzas divided by 3 people, 4/3 or 1 1/3 pizzas per person. If there are 4 people and 4 pizzas, each person gets 1. And then it's going to keep going down, right? More people means less pizza for each person, right? So if there are 5 people, then we're going to have 4/5 of a pizza, 4 pizzas divided by 5 people. And now you can figure out how the rest of this is going to go, right? So we have 4 divided by 6, which is the same as 2/3. For 7 people, we have 4/7 of a pizza. And then for 8 people, that will be 4 divided by 8, or a half a pizza for each person. So let's go ahead and plot that on a graph. So on the horizontal axis, I have a grid that is a number of people for the horizontal axis, and then the vertical axis is how many pizzas for each person. So for 1, it should be 4. For 2, it should be 2. For 3, it's going to be 1 1/3. I just have to approximate that. For 4, it should be 1. For 5, it will be 4/5. 6 is 2/3. 7 is 4/7. And then 8 is a half. So it's kind of off by a little bit, I think, especially near the end, but that's basically how this is going to go. And it makes sense, right? If we have an increasing number of people, we're going to have less pizza for each person. So the amount of pizza for each person is going down as the number of people attending the party increases. What's interesting about this situation is that it's not straight. Our graph isn't like a straight line. We have a lot of experience with straight lines, but this one is not going to be a straight line. The curve is also not like a parabola or a square root function. This one is a rational function, as it turns out. And that's the kind of function that we're studying in this section. So we'll start with a little definition and then go from there. So we want to define what a rational function looks like. A rational function is a function that can be written as the quotient of 2 polynomials, p of x and q of x. So p of x is the numerator polynomial, q of x is the denominator polynomial, and that's our f of x. So taking a look at the way this is formulated, our numerator polynomial will have degree p, our denominator polynomial will have degree q, and it's important to note that our q of x is not 0, because as always our division is, we can't divide by 0. Okay, and another way of kind of stating that is that a rational function has the form p of x over q of x, where p of x and q of x are polynomials. The domain is the set of all x such that x is any real number and q of x is not 0. For the bulk of this section, we're going to assume that p of x and q of x don't have any common factors. That is, that our fractions are already simplified. Okay, so that's what a rational function is. Basically, divide 2 polynomials and you got a rational function. So what else can we say about them? We're going to start working on the graphs of these. In order to do that, we have to have a way to describe some of the behaviors of the functions. And we're going to use arrow notation for that. So I wanted to kind of revisit that. So the table here is taken from our book. The first 4 rows or so deal with what is X doing? What is the input doing? So we have X and then an arrow and then either A or an infinity sign. When we have X, an arrow, and then an A, that means X is getting close to a particular number, A, like 3 or 5 or 12. X is getting close to a particular number. When we have this superscript plus or minus, that means that it's getting close to A from either the left side or the right side, from the negative side or the positive side. Okay, to see that, we're going to an example of that. Let's take a look at 2 functions we know well. The reciprocal function, which looks like 1 over x, and the 1 over x squared function, which may be a little bit newer. So 1 over x we looked at when we talked about odd functions and in other situations. So here we could look at, let's use our 1 over x function for this. Right there, we could talk about the behavior of the function as x approaches 2 from the left side. That would be considering values of x that are smaller than 2. That superscript minus doesn't mean we're approaching -2. It means we're approaching +2, but it is from the left side. Okay, we could also speak about x approaching 2 from the right side. That would be values of x that are close to 2 but bigger than 2. Okay. We also have x approaching either positive or negative infinity. So that would be not some specific value. So here we could talk about in our 1 over x squared graph, we could think about x approaching positive infinity. That would be, we talked about this with n behavior, right? So x is increasing without bound, so it's going towards the right end of the graph. For the left end, x is approaching negative infinity. So we could just say, okay, well, what are the values of x doing? And generally, we're interested in what is the function doing as x is doing something. So we can talk about what f is doing. F could be approaching positive infinity or negative infinity. That is, it increases without bound or decreases without bound. We discussed that when we did n behavior of polynomials, okay? F could approach a particular value. Okay, so the output could approach a certain number as x is approaching something. All right, so let's try that with our 2 examples that we have here. So we could describe the behavior of these graphs. So we could say, okay, for our f, these are both called f. Let me take the one on the right and call it g, just so we won't get confused. So our 1 over x function will be f. As x approaches negative infinity or x approaches positive infinity, f of x approaches 0. So here we have f approaching a particular value. Okay, we could say a little bit more about it if we wanted to be more specific. We could say f of x approaches 0 from the right side, that is through positive values, as x approaches positive infinity. We could say f of x approaches 0 through negative values. So it's getting close to 0, but is negative as x is approaching negative infinity. Okay, for g, we could say as x approaches negative infinity or x approaches positive infinity, f of x is approaching 0. And we could be really specific about it and say it's approaching 0 through positive values. Okay, you'll notice that both of these functions are discontinuous at the origin. There's a break in the graph there, so we have a way of talking about that as well. For g, we could say as x approaches 0 from the left side, or x approaches 0 from the right side, f of x is approaching positive infinity. So as x approaches 0 from the negative side or approaches 0 from the positive side, f of x is approaching positive infinity. That's actually g, I'm sorry. The function on the right is g of x. G of x is approaching positive infinity. For f, though, it's approaching two different infinities. So for f, what can we say? As x approaches 0 from the left side, we're talking about the circled part of the graph now, f of x will approach negative infinity. Okay, as x approaches 0 from the plus side, as x is approaching 0 from the plus side, then our f of x's will approach positive infinity. So this arrow notation is useful and is helpful as a way of describing graphs. Like I said, we used it some to talk about the end behavior for polynomials. We'll continue to use it here for talking about important features on graphs of rational functions. Okay, so the next thing to talk about is the idea of asymptotes. And that's a funny sounding word, so that's good. There's horizontal and vertical asymptotes for these rational functions. We're going to talk about vertical asymptotes first. A vertical asymptote is a vertical line that the graph gets really close to. As x gets really close to that vertical line, the f of x's either increase or decrease without bound. For the f and g that we were just discussing, the y-axis, the line x equals 0, is a vertical asymptote. Okay. Vertical asymptote. That's a vertical line that as x gets close to, the f of x is either increase or decrease without bound. Okay, so definition from our book. A vertical asymptote of a graph is a vertical line, so its equation looks like x equals a constant, where the graph tends towards either positive or negative infinity as the inputs approach a. So we write as x gets close to a, f of x approaches infinity, or as x gets close to a, f of x gets close to negative infinity. How this looks on the picture, here the vertical dashed line is going to be the asymptote. We can have it increasing from the right side towards positive infinity. It could increase towards positive infinity on the left side. The other two possibilities, decrease towards negative infinity from the right or left. And then you can see that down below we've used the arrow notation to describe that. So a key feature of rational functions is that they have those vertical asymptotes. Unlike polynomials, we saw that polynomials were continuous everywhere. They didn't have any breaks or gaps or anything. A rational function is going to have those vertical asymptotes. Okay, so this graphic is repeated from the prior page, so you don't have to worry about that. So we need to see, based on the formula for the function, how do you go about finding what those asymptotes are? It turns out that the asymptotes come from the zeros of the denominator. Remember, our f of x is p of x over q of x, and so it'll be the zeros of q of x. Okay, so let's try it. So here, first of all, for our function f of x, which is 2 over x squared minus 9, if you factor that denominator, set it equal to 0, we'll have x plus 3x minus 3 equals 0. So the two asymptotes will be at x equals negative 3 and x equals positive 3. So remember, with asymptotes, they're lines, right? And so you want to write down these as equations of lines. You want to see, as I've done them here, if you just wrote down negative 3 and 3 as two numbers, then that's not quite right. When you want to write down an asymptote, you want to write down the equation of a line. So make sure you're writing x equals this and x equals that. Okay, so let's try that again. For g, we have, it doesn't matter what the numerator is. That's going to tell us something different. The denominator here, x squared minus x minus 6, So let's set that equal to 0. And then for this one, luckily we can factor. It'll be x minus 3, x plus 2 equals 0. So either x equals 3 or x equals negative 2. So those are going to be the equations of our vertical asymptotes. Okay, for h of x here, that's 2 over x squared plus 1. Our denominator, x squared plus 1, you'll notice that that is never equal to 0, right? For finding domains, we want to know the set of x's such that the output is a real number. So for this, we won't have any complex x's, okay? So x can't be I, for example. So x squared equal negative 1 is not going to have a real number solution. So this won't have any vertical asymptotes when we get around to drawing the graph. Okay. If you haven't done it yet, you should take a minute and try this on this next set of these. So you should pause the video at this point and then see about finding the asymptotes for each of these 3 functions that we have here. Okay, so try that. All right, so here we have in the denominator x plus 8 and x minus 2. So our asymptotes will be at x equals negative 8 and x equals positive 2. So there's our 2 asymptotes. All right, so for this next one, we have x squared minus 7x plus 12 in the numerator, and then x squared minus 6 in the denominator. So x squared minus 6 equals 0 means that x squared equals 6, and so x has to be plus or minus square root 6. So x equals minus square root 6, or x equals plus square root 6. Okay, we have more. For this next one, we have x squared minus 10x plus 25. We'll set that equal to 0. And then this thing is a perfect square, actually, right? This will be x minus 5 squared equals 0. So x has to equal 5. So this one, there will only be one vertical asymptote. All right, so that has been a quick look at finding some vertical asymptotes. Not every rational function, as we saw, has a vertical asymptote, partly because the denominator maybe is just never equal to 0, or potentially because there's a 0 of the denominator that is also the 0 of the numerator. Our next example will show that. All right, so let's take a look at this function f. Again, our goal would be to find the vertical asymptotes for this function. The numerator is x squared minus 9. The denominator is x squared minus 7x plus 12. So our first task would be to factor that denominator. So we would get x minus 3, x minus 4. Notice, though, when we factor the numerator, this was a non-issue for the other examples that we did. Notice that when we factor the numerator, that the numerator and denominator now have a common factor of x minus 3. So that would divide out, leaving us x plus 3 over x minus 4. So when you have a situation like this, there won't be a vertical asymptote at 3, because, as you saw, it was divided out. It's going to turn out that the behavior of our original f will act like x plus 3 over x minus 4, except that it is undefined at 3. So we'll draw the graph of this later. It's going to end up having a hole in the graph at 3, but it won't have a vertical asymptote. So we'll see the graph of this one in a little while, and we'll see that it's got a hole, but not a vertical asymptote. In the earlier examples, I had chosen them so that there wouldn't ever be that situation arising. So you should always check the numerator and make sure that there aren't any factors of the numerator that are also factors of the denominator. Okay. All right, so the issue of vertical asymptotes is really close to the issue of the domain for a rational function. The domain on a rational function includes all real numbers except those that would cause the denominator to equal 0. So check and see what's going to make the denominator 0, and whatever that is, it's going to be excluded. So we saw here that the vertical asymptotes would be at -8 or at 2. And so those are going to be the exclusions. If you like, to try to figure out the interval notation for this, the whole real number line runs from -infinity to infinity. That's the whole thing. This thing is going to have a hole in it right at -8, okay, because we have to kick out -8 from the domain of f, and then also 2. 2 is not going to be in the domain of f. So what's left? Everything from -infinity up to -8, and then I'm going to use a round parenthesis because that's not included, union to join it to the next interval, -8 to 2, union, and then finally the last piece, which will be 2 up to +infinity. Okay, and that will be our domain for our f, written in interval notation. Okay. In that earlier example, we saw one of the factors canceled out. That led us to that hole in the graph, which is what's called a removable discontinuity. That happened back here. This thing at 3, that was a removable discontinuity. It's called that because if we just redefined our function f to change the value at 3 or give it a value at 3, then the graph could be made to be continuous. So it's called a removable discontinuity. Okay, so here, let's try an example. It says find the vertical asymptotes and removable discontinuities of the graph of this function shown here. So let's see that. So to do that, the first thing I'm going to want to do is just factor everything I can. So x squared minus 25 factors as x minus 5, x plus 5. And then the denominator, I can see there's a common factor. We'll be able to take that out. Okay, so let's do that. We'll see what's left. X comes out. That will leave x squared minus 6x plus 5. All right, and so now we need to try to factor that quadratic. So two numbers that multiply to 5 and add up to -6, same sign, both negative. That sounds like x minus 1 and x minus 5. Okay, so then we can rewrite our f of x as x minus 5, x plus 5 in the numerator. And then in the denominator, we'll have x, x minus 1, x minus 5. All right, so there's going to be one removable discontinuity. So it says find vertical asymptotes. So the vertical asymptotes will be x equals 0, so the y-axis, and then x equal 1. And then there will be a removable discontinuity at x equal 5. All right, so that does it for this video. We, of course, have more examples to do, and we will continue those in our next video. In the meantime, let me know if you have any questions, and have a great day.